4 billion light-years from Earth, something extraordinary pulses in the darkness. The blazar OJ 287 has been flaring with clockwork precision since humans first photographed it in 1891. Every 12 years, like cosmic clockwork, it erupts with a double burst of energy. Each flare releases more light than 1 trillion suns, outshining the entire Milky Way galaxy. Scientists studying this distant beacon discovered something that shouldn't exist according to simple physics. At the heart of OJ 287 sit two supermassive black holes locked in orbital embrace. The larger one contains 18.35 billion times the mass of our Sun. Its companion, though smaller, still weighs in at hundreds of millions of solar masses. They orbit each other once every 12 years, and as the smaller black hole punches through the accretion disk of its massive partner, it triggers those brilliant flares we see across billions of light-years. This isn't a curiosity confined to one distant corner of the universe. Right now, across the cosmos, supermassive black holes are spiraling toward collision. Some mergers completed millions of years ago, their gravitational waves still traveling through space toward us. Others are just beginning their billion-year dance. Understanding what happens when these titans collide reveals fundamental truths about how galaxies form, how the universe evolves, and the nature of gravity itself. The dance begins. 4 billion years from now, our night sky will transform in ways that would terrify and amaze any human who could witness it. The Andromeda galaxy, that faint smudge of light visible to the naked eye on autumn evenings, barely distinguishable from a dim star unless you know where to look, will dominate the heavens. What appears today as a distant island of stars, 2.5 million light-years away, will loom impossibly large, its spiral arms stretching across our view like luminous rivers. The galaxy will occupy a patch of sky dozens of times wider than the full moon, its core blazing bright enough to cast shadows at night. This isn't imagination or speculation about Andromeda's motion. Astronomers using the Hubble Space Telescope have tracked individual stars in Andromeda, measuring how they move across the sky over years of observation. Combined with spectroscopic measurements of Andromeda's velocity along our line of sight, these observations reveal the full three-dimensional motion of our neighboring galaxy through space. Andromeda is approaching us at 110 kilometers per second, nearly 250,000 miles per hour. For decades, astronomers assumed this meant collision was inevitable, but recent studies from 2024 and 2025, incorporating data from the European Space Agency's Gaia spacecraft, have complicated that certainty. When researchers factor in the gravitational effects of nearby galaxies, particularly the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, the calculations change. The Large Magellanic Cloud's gravity may tug the Milky Way slightly out of Andromeda's path. Current models suggest roughly a 50% chance the galaxies will collide, and a 50% chance they'll swing past each other in a near miss. If they do collide, it won't be for at least 8 billion years, rather than the previously predicted 4 billion. The universe, it seems, holds more uncertainty than we once thought. At this velocity, the distance between galaxies shrinks by roughly 1 light-month per century. Over millions of years, the separation decreases dramatically. In 4 billion years, the first close passage will occur. The word collision conjures images of destruction, of stars smashing into each other in cataclysmic explosions, of worlds consumed in fire. But the reality is far stranger and more subtle. Galaxies are mostly empty space, vast, profound emptiness interrupted by occasional motes of matter. The average distance between stars in the Milky Way measures about 4 light-years. Our Sun's nearest neighbor, Proxima Centauri, lies 4.24 light-years away. That's 25 trillion miles of empty space between adjacent stars. If two galaxies do merge, their stars pass by each other like ships in an endless ocean. You could run the simulation 1,000 times and perhaps not see a single stellar collision. A star has better odds of winning the cosmic lottery multiple times than hitting another star during a galactic merger. The stars themselves will survive the collision intact, unharmed, merely redirected into new orbits by the gravitational forces at play. But gravity doesn't care about emptiness. Gravity operates across the void, an invisible architecture shaping the motions of every object. If the Milky Way and Andromeda do interpenetrate, whether in a full merger or a close encounter, gravitational forces will reshape both galaxies fundamentally. Stars will be flung into new orbits, their trajectories forever altered by the gravitational tides. Some will be ejected entirely, cast out to wander the void between galaxy clusters at velocities exceeding 1,000 kilometers per second. Cosmic exiles, forever separated from their birth galaxies. Vast clouds of gas and dust will collide with actual physical impact. Unlike stars, which are separated by such enormous distances that they never touch, gas clouds are diffuse and extended. When clouds from two galaxies meet, they compress, shock heat, and form dense cores. These compressed regions collapse under their own gravity, triggering bursts of star formation. The collision zones light up with the blue-white brilliance of massive young stars. Supernovae soon follow the death explosions of short-lived massive stars, adding energy and heavy elements to the interstellar medium. A merger, if it occurs, will unfold over hundreds of millions of years, a slow-motion cosmic ballet invisible to any individual observer across multiple lifetimes. If you could somehow watch the collision from beginning to end at normal speed, you'd need to live millions of times longer than a human lifespan. Even if you compressed the entire merger into a 24-hour time-lapse movie, each second would represent thousands of years of real time. For the sake of understanding what happens when supermassive black holes merge, the actual focus of our exploration tonight, let's consider the scenario where Andromeda and the Milky Way do collide, as they still might. The physics of that merger teaches us about black hole collisions happening throughout the universe, regardless of what ultimately happens in our own cosmic neighborhood. In a collision scenario, first contact would occur when the galaxies make their first close passage. They won't merge immediately. Instead, they'll swing past each other, their mutual gravity pulling them into distorted shapes. Long tidal tails, streams of stars pulled out by gravitational forces, will trail behind each galaxy like the tail of a comet. These tails can extend for hundreds of thousands of light years into intergalactic space. After this first passage, the galaxies will separate again, moving apart for tens of millions of years before their mutual gravitational attraction pulls them back together. The second passage will be closer than the first. The galaxies will interpenetrate more deeply, their cores passing through each other's disks. More tidal disruption. The galaxies emerge even more distorted, their beautiful spiral structure demolished, replaced by chaotic swarms of stars in complex orbits. A third passage follows, then perhaps a fourth. Each collision strips away more angular momentum, the tendency of objects to rotate until finally the galaxies can no longer escape each other's gravity. They settle into a single, merged system, a process taking perhaps 1 billion years from first contact to final coalescence. At the center of the Milky Way sits Sagittarius A*, our galaxy's supermassive black hole. Located 26,000 light-years from Earth, in the direction of the constellation Sagittarius, this monster contains 4.3 million solar masses, compressed into a region smaller than Mercury's orbit. The Event Horizon Telescope imaged its shadow in 2022, revealing the bright ring of hot gas orbiting just outside the event horizon. Despite its enormous mass, Sagittarius A times is relatively quiet as supermassive black holes go, accreting matter slowly and emitting modest amounts of radiation. Andromeda harbors its own central monster, weighing in at roughly 140 million solar masses, over 30 times more massive than our black hole. This size difference reflects Andromeda's greater overall mass. Andromeda contains perhaps 1 trillion stars, compared to the Milky Way's few hundred billion. Its central black hole grew correspondingly larger through accretion and previous mergers. If the galaxies do merge, these two objects will embark on their own journey toward each other. Initially, they'll be separated by hundreds of thousands of light years, each occupying what was once the center of its parent galaxy. The newly merged galaxy astronomers have dubbed it Milkomeda. In this scenario would be a chaotic environment for many millions of years after the final coalescence. Stars from both galaxies will swarm in complex orbits, their motions no longer organized into the neat spiral structure of their parent galaxies. Gas clouds will shock heat to millions of degrees where they collide, emitting X-rays and driving galactic winds. Supernovae will explode at elevated rates, triggered by the burst of star formation. Active galactic nuclei regions around the accreting black holes will blaze across the electromagnetic spectrum as material falls inward. And somewhere in all this chaos, 2 supermassive black holes will begin their slow approach. The mechanism that brings them together was first described by the brilliant astrophysicist Subrahmanyan Chandrasekhar in 1943, during the middle of World War II. Working at the University of Chicago, Chandrasekhar, who would later win the Nobel Prize in Physics for his work on stellar evolution, derived the mathematical framework for what he called dynamical friction. The term friction is somewhat misleading because it has nothing to do with friction as we normally understand it: surfaces rubbing together, generating heat, slowing motion through direct physical contact. Instead, dynamical friction is a gravitational process, elegant in its simplicity and profound in its consequences. It operates through pure geometry and mathematics. Invisible forces operating across vast distances of empty space. Picture a supermassive black hole containing 100 million solar masses moving through a sea of stars. The black hole travels at perhaps 200 kilometers per second relative to the average stellar motion, slow by cosmic standards, but 400 times faster than a rifle bullet. As this behemoth moves through the galaxy, it passes near countless stars. Near, in astronomical terms, might mean thousands of light-years distances where the black hole's gravity is gentle but still significant. Consider a single such encounter. A star orbits the galactic center on its own path when a massive black hole approaches from an angle. The black hole's gravity reaches out across thousands of light years, tugging on the star. The star's trajectory curves toward the black hole. As it swings past, the star accelerates, much like a spacecraft using a planetary flyby for a gravitational assist. This is the gravitational slingshot effect, used routinely by space mission designers to boost spacecraft to higher velocities. But here it operates on vastly larger scales. The star, after its encounter with the black hole, moves faster than before. It has gained kinetic energy. Conservation of energy demands that this energy came from somewhere. It came from the black hole's motion through the galaxy. The black hole, having accelerated the star, must itself decelerate slightly. It's like a massive ship passing through water. The ship pushes water molecules aside and forward, imparting momentum to the water while losing a tiny amount of its own momentum. For a ship, the effect is negligible, because even a large ship is far lighter than the volume of water it moves through. But aggregate billions of water molecules, and the drag becomes noticeable. Similarly, one star has negligible effect on a supermassive black hole. A 100 million solar mass black hole losing momentum to a 1 solar mass star barely notices the interaction. The velocity change is infinitesimal. But a supermassive black hole moving through a galaxy interacts gravitationally with billions of stars over millions of years. Each interaction steals a microscopic amount of momentum. The cumulative effect becomes dramatic. Mathematical analysis shows the deceleration rate depends on several factors. The black hole's mass matters more. Massive black holes experience stronger dynamical friction because they gravitationally affect more stars per unit time. The density of surrounding stars matters. Denser environments provide more targets for interactions. The black hole's velocity matters, but counterintuitively, faster-moving black holes experience weaker dynamical friction. This is because faster black holes spend less time near each star, reducing the strength of each interaction. The formula Chandrasekhar derived shows that dynamical friction force is proportional to the black hole's mass squared, the density of surrounding matter, and inversely proportional to the black hole's velocity squared. This creates interesting dynamics. As dynamical friction slows the black hole, the friction becomes more efficient, accelerating the slowdown in a positive feedback loop. But eventually, the black hole sinks to the galactic center, where stellar density peaks and the process stabilizes. Over millions of years, dynamical friction acts like a cosmic brake, draining the black hole's momentum and causing it to spiral inward toward the gravitational center of the merged galaxy. The timescale varies depending on the initial conditions, the black hole's starting position, velocity, mass, and the galaxy's structure. But for typical conditions in major galaxy mergers, dynamical friction brings both black holes from their starting positions, hundreds of thousands of light-years apart, to within a few thousand light-years of the merged galaxy's center in approximately 500 million years. Both black holes experience this process simultaneously. Both sink toward the center, following spiral trajectories that gradually tighten. As they approach the central region, they begin to gravitationally influence each other directly. When their separation drops below a few thousand light-years, their mutual gravitational attraction becomes stronger than the attraction to the distributed stellar mass of the galaxy. At this critical point, they form a bound binary system, orbiting around their common center of mass, a point determined by their mass ratio. Now, they're no longer two independent objects wandering through the galaxy. They're locked in gravitational embrace, partners in an orbital dance that will continue for millions more years. The orbital period at this early stage might be 100,000 years or more. They're still separated by distances comparable to the size of a small galaxy, but they're bound to each other, their fates now intimately connected. The orbital period depends on their separation and combined mass. Following Kepler's laws, the same laws that govern planetary orbits, but applied to vastly larger masses and scales. At a separation of a few hundred light-years, with a combined mass of perhaps 200 million solar masses, they might orbit each other once every few 100,000 years. The orbital velocity at this separation would be modest, perhaps 50 kilometers per second, slow by astronomical standards. As they spiral closer, driven by continuing dynamical friction, the orbital period decreases according to Kepler's third law. The square of the orbital period is proportional to the cube of the separation. Halve the separation, and the orbital period decreases by a factor of about 2.8. The orbital velocity increases as they get closer. Tighter orbits require faster motion to balance the stronger gravitational attraction. When they're 10 light-years apart, they might orbit once every few thousand years. The orbital velocity has increased to perhaps 500 kilometers per second, still only 1/6 of 1% of light speed, but fast enough to produce noticeable relativistic effects. The black hole's gravitational fields begin to interact more strongly, and the simple two-body dynamics become complicated by relativistic corrections to Newtonian gravity. At 1 light-year separation, the period could be measured in centuries, maybe 500 years per orbit. The orbital velocity climbs toward 5,000 kilometers per second, over 1% of light speed. General relativistic effects become important. The orbit precesses its orientation, slowly rotates due to the curvature of spacetime. This precession is similar to, but far more pronounced than the relativistic precession of Mercury's orbit around the Sun, which amounts to 43 arcseconds per century and provided one of the first confirmations of general relativity. Throughout this approach, dynamical friction continues to operate, though its nature evolves. At large separations, when the black holes are still thousands of light years apart, individual stars interact with each black hole separately. The friction on each black hole is independent, and they spiral toward the galactic center on separate trajectories that happen to intersect near the center. But once they form a bound binary, the dynamics change. Now stars and gas interact with the binary as a system. These three-body interactions, a star encountering a pair of black holes, are complex and chaotic. The outcomes depend sensitively on the star's trajectory, velocity, and impact parameter, how close it passes to the binary. Some stars receive large velocity kicks that accelerate them to escape velocity. Other stars trade energy and angular momentum with the binary in more subtle ways, removing small amounts from the orbit over each encounter. Gas behaves differently because it can dissipate energy through collisions and radiation, but it too can transport energy and angular momentum away from the binary. The net effect of all these interactions is that the binary loses energy and angular momentum while the surrounding matter gains both. The binary orbit shrinks, the orbital period decreases, the black holes spiral closer and closer together, accelerating as they approach. The slowing of giants. Dynamical friction represents one of nature's more counterintuitive mechanisms. We're used to friction involving contact surfaces rubbing together, generating heat, slowing motion through direct physical interaction. Gravitational friction works through pure geometry and mathematics, invisible forces operating across vast distances. The mathematical description begins with Chandrasekhar's 1943 paper, a masterwork of astrophysical analysis. He derived equations showing how a massive object moving through a distribution of lighter objects experiences a drag force proportional to its mass, the density of surrounding matter, and inversely related to its velocity squared. The faster the object moves, the less effective dynamical friction becomes. The denser the surrounding environment, the stronger the braking effect. For supermassive black holes in merging galaxies, the numbers are staggering. Consider two galaxies, each containing 100 billion stars, merging together. In the aftermath of the merger, the central region where the black holes are located contains perhaps 10 billion stars within a few thousand light years. Each star has an average mass similar to our Sun. The total stellar mass in this central region exceeds 10 billion solar masses. As a supermassive black hole containing, say, 100 million solar masses moves through this environment, it interacts with thousands of stars per year. Each interaction is gentle. The black hole passes light years away from the star, but gravity operates across these distances. The star's trajectory curves slightly. The black hole's trajectory curves slightly in the opposite direction. Multiply by thousands of interactions per year over millions of years, and the cumulative effect becomes enormous. Research by astrophysicist Monica Colpi at the University of Milano Bicocca has shown that dynamical friction can reduce a binary's separation from 100,000 light-years to 10 light-years in approximately 500 million years, given typical conditions in merged galaxies. The process accelerates as the black holes get closer because their gravitational influence on surrounding matter increases. At 1,000 light-year separation, they might lose distance at 10 light-years per million years. At 100 light-year separation, the rate could be 5 light-years per million years. But dynamical friction has consequences beyond simply bringing black holes together. As the binary loses energy to surrounding stars, those stars gain energy. Many are accelerated to high velocities, sometimes exceeding the galaxy's escape velocity. Over the course of the merger, the binary can eject billions of stars from the galactic core. This creates an observable signature, Merged galaxies often show depleted central regions, cores with fewer stars than expected. Astrophysicists call these core scouring effects. The ejected stars carry away not just kinetic energy but also angular momentum. This is crucial because angular momentum is conserved in isolated systems. For the binary to shrink to reduce its orbital radius and angular momentum, something else must carry that angular momentum away. Stars do this job admirably. They arrive with their own angular momentum, interact gravitationally with the binary through complex three-body encounters, and depart with modified angular momentum. The net transfer allows the binary to shrink. Gas plays a similar role. Though the physics differs, gas can't be ejected as easily as individual stars, but it can be heated and dispersed. As black holes orbit each other, they stir the surrounding gas, driving shocks and turbulence. The gas heats to millions of degrees and may be driven outward in galactic winds. Some gas falls into the black holes, fueling accretion and producing brilliant luminosity. The energy for these winds and this luminosity ultimately comes from the binary's orbital energy, continuing the shrinkage. Numerical simulations by teams around the world have visualized this process. The simulations start with two galaxies on collision course, each containing a central supermassive black hole. They follow the evolution over billions of simulated years. The galaxies merge, the black holes sink toward the center. Stars swarm in chaotic orbits. The black holes form a binary. The binary hardens astrophysicist jargon for orbital shrinkage. Eventually, in the simulations, the black holes approach a separation of about 1 parsec. Then, something strange happens. The shrinkage slows dramatically. Sometimes it stops entirely. The binary stalls at roughly 1 parsec separation, orbiting endlessly without further progress toward merger. This phenomenon has plagued astrophysicists for decades. They call it the Final Parsec Problem. The Final Parsec Problem. In 1980, two astrophysicists named Mitchell Begelman, Richard Blandford, and Martin Rees published a paper that would haunt the field for the next 4 decades. They calculated what should happen when two supermassive black holes reach a separation of roughly 1 parsec, 3.26 light-years. Their conclusion was troubling. At this distance, dynamical friction becomes ineffective, and the black holes should stall in orbit around each other for longer than the age of the universe. The physics is straightforward but sobering. Dynamical friction requires surrounding matter. Stars must pass near the binary to interact gravitationally and carry away energy and angular momentum. But as the binary shrinks, it clears out the central region. Stars that pass too close to the binary receive gravitational kicks that accelerate them to high velocities. Many are ejected from the galaxy entirely. Others are flung into distant orbits, from which they'll take millions of years to return. This carves out a depleted region around the binary. Think of it as a gravitational exclusion zone, a spherical volume with radius approximately equal to the binary's separation. Inside this zone, the stellar density drops dramatically. Fewer stars means fewer interactions. Fewer interactions means less energy and angular momentum transfer. The dynamical friction that brought the black holes from 100,000 light-years separation to 1 parsec loses its power. The numbers are stark and unforgiving. Calculations showed that once a binary reaches the final parsec, further shrinkage through dynamical friction alone would require a timescale of 10 to 100 billion years, possibly longer, depending on the specific conditions. The universe is only 13.8 billion years old. This means that supermassive black hole binaries should be common throughout the cosmos, frozen at parsecant scale separations, never completing their merger. They would orbit each other essentially forever from a cosmological perspective, eternal partners unable to consummate their gravitational embrace. This prediction created a significant problem for cosmology and our understanding of galaxy evolution. Galaxy mergers are common. We see them happening throughout the universe at all cosmic epochs. Modern cosmological simulations, which follow the evolution of dark matter and galaxies from shortly after the Big Bang to the present, show that essentially every large galaxy has undergone multiple mergers over cosmic history. If every merger produces a stalled binary, then every large galaxy should contain either a binary or multiple black holes from multiple mergers that never completed. The implications would be profound. Galactic centers would be cluttered with black holes, pairs, or even triplets or quadruplets of supermassive black holes orbiting each other at parsecant scale separations. These configurations should be relatively easy to detect through their distinctive signatures. Periodic variations in emission as the black holes orbit. Spectroscopic features showing multiple velocity components. Possibly even direct imaging with very long baseline interferometry at radio wavelengths. But observations didn't support this prediction. While astronomers found some binary candidates, systems showing suggestive evidence of two black holes, they weren't ubiquitous. Binary candidates remained rare, curiosities rather than the norm. Either the theory was missing something important, or the observations were missing most binaries for some reason. Moreover, theoretical models of black hole growth face serious challenges if mergers couldn't complete. Supermassive black holes grow through two primary channels, accretion of gas and mergers with other black holes. If mergers can't complete, then mergers contribute nothing to black hole growth. Every supermassive black hole we observe, including monsters like the 18 billion solar mass object in OJ 287, or the 66 billion solar mass giant in the galaxy Holmberg 15A, would need to have grown entirely through accretion. Growing a black hole to billions of solar masses through accretion alone is possible, but requires very specific conditions maintained over cosmic timescales. The gas must lose angular momentum efficiently to fall inward rather than settle into a stable orbit. Accretion can't proceed too fast, or radiation pressure from the infalling material pushes gas away, creating a self-regulating feedback mechanism called the Eddington limit. Even at the Eddington limit, the maximum sustainable accretion rate growing a black hole from a stellar mass seed of perhaps 100 solar masses to a billion solar masses requires approximately 800 million years of continuous accretion. That's feasible over the 13.8 billion year age of the universe, but it requires the black hole to accrete continuously at maximum rate with no interruptions for most of a billion years. Any interruptions extend the growth time, and we observe billion solar mass black holes and quasars at redshifts above 7, meaning we see them as they were less than 800 million years after the Big Bang. Growing them through accretion alone requires starting from larger seeds or accreting at super Eddington rates, both of which are possible but add complexity to the models. Mergers offer an attractive alternative or complement to accretion. A 1,0,0 million solar mass black hole that merges with another 1,0,0 million solar mass black hole instantly becomes 200 million solar masses, minus a few percent, radiated as gravitational. Merge again and reach 400 million. After 10 mergers, you exceed 100 billion solar masses. The growth is exponential rather than linear, potentially much faster than accretion, but only if the mergers complete. If binaries stall at the final parsec, this growth channel shuts down. Black holes would be limited to growth through accretion, constraining how quickly they can reach the enormous masses we observe. The mystery deepened dramatically in June 2023, when an international collaboration of scientists operating pulsar timing arrays announced a groundbreaking detection that would transform our understanding of this problem. The North American Nanohertz Observatory for Gravitational Waves NANOGrav, along with their European, Australian, and Chinese counterparts, reported evidence of a gravitational wave background permeating the universe. This wasn't a single detection like LIGO's observations of individual black hole mergers. Instead, it was something more subtle and profound. A cosmic hum, a background signal present in all their data, coming from all directions in space. The signal showed the characteristic correlations predicted for gravitational waves. Pulsars, separated by larger angles on the sky, showed weaker correlations than nearby pulsars, exactly matching the mathematical pattern called the Hellings-Downs correlation that gravitational waves produce in pulsar timing data. The signal strength matched predictions for the combined gravitational wave emission from hundreds of thousands of supermassive black hole binary mergers occurring throughout the observable universe. The spectrum, how the signal strength varies, with frequency aligned with theoretical expectations for a population of merging binaries. Lower frequencies showed more power, consistent with many massive binaries in the early stages of in-spiral, while higher frequencies showed less power, consistent with fewer binaries in the final, rapid in-spiral before merger. Gravitational waves carry energy and angular momentum away from binary systems. For stellar mass black holes, the kind detected by LIGO, typically containing 10 to 100 solar masses, gravitational wave emission dominates the late stages of in-spiral. Once the black holes reach a separation, where orbital velocities approach a significant fraction of light speed, they radiate gravitational waves powerfully enough to drain the orbit and cause merger within hours or days. But supermassive black holes are different. Their enormous masses mean they orbit much more slowly at the same separation. A supermassive black hole binary at 1 parsec separation might have an orbital velocity of a few hundred kilometers per second, fast by everyday standards, but less than 1% of light speed. At such modest velocities, gravitational wave emission is weak. Calculations showed it would take billions of years for gravitational waves alone to shrink the orbit from 1 parsec to the point where merger becomes inevitable. Here was the paradox. NANOGrav detected gravitational waves from merging supermassive black holes, proving that these mergers happen. Yet the Final Parsec Problem suggested they shouldn't happen or should be exceedingly rare. Something was missing from the models. Some mechanism or combination of mechanisms must be operating that astrophysicists hadn't fully accounted for. The search for solutions to the Final Parsec Problem became one of the driving questions in astrophysics over the past 2 decades. Multiple teams proposed different mechanisms. Each had observational predictions. Each had theoretical challenges. The question wasn't whether supermassive black holes merge. NANOGrav proved they do. The question was how, crossing the Final Parsec. The proposed solutions to the Final Parsec Problem fall into several categories, each involving different physics and making different predictions about what we should observe when we look at merging galaxies. One promising mechanism involves gas. While stars can be ejected from the depleted core region, gas is more resilient. In many galaxy mergers, particularly mergers involving gas-rich spiral galaxies, substantial amounts of gas survive in the nuclear region. This gas doesn't orbit in simple trajectories like stars. Instead, it forms a circumbinary disk, a rotating disk of gas surrounding both black holes. The physics of circumbinary disks is complex and beautiful. As the binary orbits, its gravitational field creates torques on the disk. These torques drive spiral density waves in the gas, structures that propagate outward through the disk like ripples on a pond. The binary, having imparted this angular momentum to the waves, must lose angular momentum to conserve the total. Moreover, each black hole typically has its own small accretion disk, fed by gas flowing in from the larger circumbinary disk. Gas streams can flow from the circumbinary disk into the mini-disks around each black hole, following complex trajectories shaped by the rotating gravitational field of the binary. This gas transport removes mass and angular momentum from the system. Research by astrophysicist Dong Lai at Cornell University and his collaborators has shown that under favorable conditions, circumbinary disks can drive binary and spiral on timescales of tens of millions of years. This is fast enough to solve the Final Parsec Problem. The key is having sufficient gas mass and the right viscosity properties to allow efficient angular momentum transport. The observational prediction is clear. Galaxies hosting supermassive black hole binaries actively crossing the final parsec should show evidence of substantial gas in their nuclear regions. They should also show specific signatures in their spectra patterns of emission lines from gas moving in the complex gravitational field of the binary. Several candidate systems showing these signatures have been identified, though definitively confirming a binary remains challenging at such small angular scales. A second mechanism involves three-body interactions, but with a twist. Rather than stars, this solution invokes a third supermassive black hole. In the dense cosmic web where galaxies cluster together, triple galaxy mergers aren't uncommon. Sometimes two galaxies begin merging, their central black holes forming a binary, when a third galaxy arrives and joins the merger. Laura Blecka at the University of Florida has studied these scenarios extensively. Her simulations show that a third black hole can dramatically speed up the evolution of the existing binary. The three-body gravitational interactions are chaotic and violent. The lightest of the three black holes often receives a large gravitational kick and is ejected from the system at high velocity. The remaining two, having exchanged energy and angular momentum with the ejected third, find themselves on a much tighter orbit. In some configurations, all three black holes eventually merge, but through a series of binary mergers, rather than a simultaneous triple merger. The first two to merge form a recoiling remnant, more on recoil later. The third eventually catches up and merges with this remnant. The overall timescale for complete merger can be reduced from billions of years to hundreds of millions of years. Evidence for triple systems is accumulating. Several galaxies show three distinct active galactic nuclei, bright regions powered by accreting supermassive black holes within a few thousand light-years of each other. These represent the early stages of triple interactions. Finding systems where the three black holes are within parsecs of each other remains a major observational challenge, but upcoming instruments with higher angular resolution should help. But perhaps the most intriguing solution emerged in 2024 from Gonzalo Alonso Alvarez at the University of Toronto and his collaborators. They proposed that dark matter, that mysterious substance comprising 85% of the universe's matter, plays a crucial role in solving the Final Parsec Problem. Dark matter doesn't emit light, doesn't absorb light, and interacts with ordinary matter only through gravity. Rotation curves of galaxies show that they contain far more mass than can be accounted for by stars and gas. Gravitational lensing reveals massive dark matter halos surrounding galaxies. The cosmic microwave background and large-scale structure of the universe both require dark matter to match observations. Near supermassive black holes, dark matter should form a spike, a region of enhanced density created by the black hole's gravity. As ordinary matter falls toward the black hole and is consumed, dark matter, which doesn't collide with itself or ordinary matter, simply orbits. Over time, the black hole's gravity draws dark matter into ever tighter orbits, creating a dense concentration. Alonso Alvarez's key insight involved a specific type of dark matter, self-interacting dark matter. While dark matter doesn't interact with ordinary matter except through gravity, it could interact with other dark matter particles. These interactions would be rare, but not infinitesimally so. When dark matter particles collide, they scatter. In the dark matter spike around a supermassive black hole binary, self-interactions give the dark matter fluid-like properties. It develops viscosity. When the binary orbits through this viscous dark matter medium, it experiences genuine dynamical friction, even in the absence of stars. The calculations showed this dark matter friction could be powerful enough to shrink the binary from 1 parsec down to the milliparsec scales, where gravitational wave emission takes over. The beauty of this solution is that it connects to other puzzles in cosmology. Self-interacting dark matter with the right interaction cross-section about 1 square centimeter per gram solves not just the Final Parsec Problem, but also explains certain features of dark matter distribution in galaxies that standard cold dark matter struggles with. It's a theory that fits multiple pieces of evidence. Testing these solutions requires observations. We need to find supermassive black hole binaries at various stages of their evolution and measure their properties. We need to detect the gravitational waves they emit and compare the strength of these waves to theoretical predictions. We need high-resolution images of galactic nuclei to map the distribution of stars, gas, and ideally, somehow, each solution makes predictions. Gas-driven in spiral should correlate with gas-rich galaxy mergers and show specific spectroscopic signatures. Three-body interactions should leave isolated high-velocity black holes, those that were ejected wandering through intergalactic space. Dark matter friction should leave an imprint on the gravitational wave spectrum, a particular pattern in how wave frequency and amplitude relate. The NANOGrav detection in 2023 provided crucial evidence. The gravitational wave background has a spectrum, a distribution of power across different frequencies. The observed spectrum matches predictions for a population of supermassive black hole binaries successfully crossing the final parsec and merging. The spectrum is slightly softer at low frequencies than the simplest models predict, which intriguingly aligns with expectations if dark matter friction is operating. But NANOGrav detected only the background, the combined signal from hundreds of thousands of binaries throughout the observable universe. To really test the solutions, we need to detect individual mergers. That requires more sensitive instruments and longer observation times. The International Pulsar Timing Array collaboration continues monitoring pulsars, accumulating data year by year. Eventually, the loudest individual sources should emerge from the background, gravitational waves. In 1916, Albert Einstein published the final form of his general theory of relativity, a radical new description of gravity. Rather than a force acting across empty space, gravity emerged from the curvature of space-time itself. Massive objects curve space-time around them, and other objects follow the straightest possible paths through this curved geometry. What we perceive as gravitational attraction is actually objects following geodesics' generalized straight lines through curved space-time. The equations of general relativity are famously complex, a set of 10 coupled nonlinear partial differential equations relating the curvature of space-time to the distribution of matter and energy. Einstein himself found exact solutions only for the simplest cases. But in examining these equations, he discovered something remarkable. They permit wave solutions. Space-time itself can ripple, and these ripples propagate outward at the speed of light. Einstein was skeptical these gravitational waves could ever be detected. The amplitude of the waves from any realistic source seemed impossibly small. A gravitational wave passing through Earth would stretch and squeeze space by a fractional amount around 10 to the minus 21st power, 1 part in 1,000 billion. Detecting such tiny distortions seemed beyond technological possibility. For decades, gravitational waves remained purely theoretical. Then, in 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, 2 neutron stars, orbiting each other with a period of 8 hours. Pulsars emit beams of radio waves like cosmic lighthouses, and the timing of pulses can be measured with exquisite precision. Hulse and Taylor tracked this binary pulsar for years, measuring how its orbital period changed over time. The orbit was shrinking. General relativity predicts that binary systems emit gravitational waves, and these waves carry away energy and angular momentum. Loss of orbital energy means the orbit shrinks. The measured rate of orbital decay matched general relativity's predictions exactly. This provided the first indirect evidence that gravitational waves exist and carry the predicted amount of energy. Hulse and Taylor received the Nobel Prize in Physics in 1993. But indirect evidence wasn't enough. Physicists wanted direct detection to actually measure gravitational waves as they passed through Earth. This required building an extraordinarily sensitive instrument, and such an instrument seemed to verge on the impossible. A gravitational wave passing through Earth would change the distance between 2 points separated by a kilometer by less than 1,000th the diameter of a proton. The Laser Interferometer Gravitational Wave Observatory LIGO consists of 2 identical facilities, one in Livingston, Louisiana, and one in Hanford, Washington. Each facility has 2 arms, each 4 kilometers long, arranged in an L shape. Laser beams travel down each arm, reflect off mirrors at the ends, and return to interfere with each other. If a gravitational wave passes through, it stretches one arm while squeezing the other, changing the interference pattern. LIGO began operations in 2002, but detected nothing for years. The original design wasn't sensitive enough. A major upgrade to advanced LIGO was completed in 2015, increasing sensitivity by a factor of 10. The upgraded detectors began observing on the 14th of September 2015. At 9 hours, 50 minutes, and 45 seconds UTC, both LIGO detectors registered a signal. The signal lasted less than a quarter of a second and swept upward in frequency from 35 Hz to 250 Hz. It had the characteristic shape predicted for merging black holes. First, a long in spiral as the black holes orbit closer together, then a brief merger phase lasting milliseconds, then a ring down as the merged black hole settles into its final configuration. Analysis revealed 2 black holes with masses around 36 and 29 solar masses spiraling together and merging 1.3 billion light-years from Earth. The merger converted 3 solar masses, 3 times the mass of our Sun, into gravitational wave energy in the final fraction of a second. The peak power output, for those brief milliseconds, exceeded the combined light output of all stars in the observable universe. This was the first direct detection of gravitational waves, confirming Einstein's century-old prediction. It was also the first direct evidence that black holes exist and can merge. The discovery earned the Nobel Prize in Physics in 2017 for Rainer Weiss, Barry Barish, and Kip Thorne, the leaders of the LIGO project. Since 2015, LIGO, together with its Italian counterpart Virgo, and more recently the Japanese detector KAGRA, has detected over 200 gravitational wave events. Most are black hole mergers, with black holes ranging from a few solar masses to over 100 solar masses. Several are neutron star mergers. Each detection adds to our understanding of these exotic objects and tests general relativity in the strong field regime, where gravity's strength approaches theoretical maxima. But LIGO can detect only stellar mass black holes. The gravitational waves from supermassive black holes oscillate far too slowly for LIGO's design. LIGO is most sensitive to frequencies between 10 and a few thousand hertz. Supermassive black hole binaries, because of their enormous masses and correspondingly large orbital separations, emit gravitational waves at frequencies measured in nanohertz billionths of a hertz. A wave with a frequency of 1 nanohertz has a period of 32 years. Detecting these ultra-low frequency waves requires a fundamentally different approach. Rather than laser interferometers, astronomers use pulsar timing arrays. Pulsars, rapidly rotating neutron stars, emit beams of radio waves from their magnetic poles. If the beam sweeps across Earth, we detect regular pulses, sometimes hundreds of pulses per second, stable enough to rival atomic clocks. A gravitational wave passing between Earth and a pulsar stretches and squeezes the space along the line of sight. This changes the travel time of pulsar signals by nanoseconds. By monitoring an array of pulsars distributed across the sky, astronomers can detect gravitational waves from their characteristic pattern of timing residuals. The North American Nanohertz Observatory for Gravitational Waves, NANOGrav, monitors 68 pulsars using the Green Bank Telescope in West Virginia and other radio telescopes. The European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array conduct similar observations. These collaborations have monitored pulsars for over 15 years, accumulating the long baseline of observations needed to detect ultra-low frequency gravitational waves. In June 2023, these collaborations announced detection of a gravitational wave background. The signal appeared in data from all 4 pulsar timing arrays, with the characteristic angular correlation pattern predicted for gravitational waves. The signal strength matched expectations for hundreds of thousands of supermassive black hole binaries throughout the universe, each emitting gravitational waves as they spiral toward merger. This detection proved that supermassive black holes do merge, overcoming whatever barriers the Final Parsec Problem presents. The gravitational wave background at nanohertz frequencies is about twice as loud as the most conservative predictions, suggesting either that supermassive black holes are more massive or more abundant than expected, or that something beyond black hole mergers contributes to the signal. Over the coming years, as pulsar timing arrays continue observations, individual loud sources should begin to stand out from the background. These will be the nearest and most massive binaries, systems like OJ-287 that we can observe electromagnetically. Combining gravitational wave observations with electromagnetic observations will provide unprecedented insights into binary evolution, testing general relativity, and probing the environments around supermassive black holes. The power of the merger. The energy released when 2 supermassive black holes merge defies human intuition and challenges our ability to comprehend vast scales. We have no everyday reference points for such power, no familiar experiences to anchor our understanding. Even comparing to astronomical phenomena we're familiar with, supernovae, solar flares, entire galaxies of stars, falls dramatically short. The merger briefly outshines the combined gravitational wave output of everything else happening in the observable universe combined. Consider the numbers carefully, because they reveal something profound about the fabric of reality itself. When LIGO detected GW150914, that first gravitational wave event from 2 stellar mass black holes merging 1.3 billion light-years away, the careful analysis revealed that 3 solar masses of material converted entirely to gravitational wave energy, not 3 solar masses of hydrogen fusing to helium like in a star, releasing a tiny fraction of mass as energy. Not 3 solar masses exploding in a supernova, converting perhaps 1% of mass to energy. 3 entire solar masses, 3 times the complete mass of our Sun, instantaneously transformed into ripples in spacetime. Einstein's most famous equation, E equals mc squared, tells us precisely how much energy this represents. Energy equals mass times the speed of light squared. The speed of light is 300,000 kilometers per second. Square that, and you get 90 trillion meters squared per second squared. Multiply by the mass of 3 suns, about 6 times 10 to the 30th kilograms, and the calculation yields 5.4 times 10 to the 47th joules. To put that in perspective, that makes even remote sense. Our Sun's total energy output over its entire 10 billion year lifetime will be about 10 to the 44th joules. The Sun fuses 600 million tons of hydrogen into helium every second, converting about 4 million tons of mass to energy through nuclear fusion. It has done this for 4.6 billion years and will continue for another 5 billion years or so. Add it all up, and you get 10 to the 44th joules. The GW150914 merger released more energy in its final fraction of a second than our Sun will emit over 5,000 lifetimes, spanning 50 trillion years. Let that sink in for a moment. Two black holes, each about 30 times the Sun's mass, spiraling together and merging, released more energy than 5,000 suns burning for their entire lifetimes. And they did it in 200 milliseconds, 1/5 of a second. The peak power output during those final moments reached 3.6 times 10 to the 49th watts. For comparison, all the stars in the observable universe combined hundreds of billions of galaxies, each containing hundreds of billions of stars, all shining simultaneously, emit about 10 to the 49th watts. For those final 20 milliseconds of GW150914, this one merger event outshone the entire visible universe by a factor of more than 3. Not in visible light, the merger produced no electromagnetic radiation, but in gravitational waves, in the actual vibration of spacetime itself. But GW150914 involved stellar mass black holes, mere bantamweights, compared to the supermassive monsters at galactic centers. When two supermassive black holes merge, the energy scales increase proportionally to their masses. A merger involving two black holes of 100 million solar masses each could convert 1 billion solar masses of energy, about 5% of the total mass, into gravitational waves. The gravitational wave luminosity scales with the fifth power of the mass, and inversely with the fifth power of the orbital period. More massive black holes, orbiting more slowly at the same separation, actually emit less power, but they orbit for much longer before merging, and the total energy released integrates this power over time. The result is that supermassive black hole mergers release millions of times more total energy than stellar mass mergers. OJ287 provides a real-world example. If the binary interpretation is correct, and recent observations continue to support this, the system contains black holes of roughly 18 billion and 150 million solar masses orbiting with a 12-year period. At such a period, the separation measures about 10,000 astronomical units, roughly 1/20th of a light year. The system is currently too far from merger for gravitational waves to dominate the evolution, but it's already radiating. Calculations for OJ287 suggest it emits gravitational waves at a power of about 10 to the 39th watts. That's 1,000,000 times the sun's electromagnetic luminosity, though still modest by gravitational wave standards. As the binary shrinks, the orbital period decreases, and the gravitational wave luminosity increases. In the final years before merger, as the orbital period drops to days, then hours, the luminosity will soar. When the binary finally merges, the event will be spectacular, even at a distance of 4 billion light-years. The merged black hole will undergo ring-down oscillations of its event horizon as it settles into a stable configuration. These oscillations emit powerful gravitational waves at characteristic frequencies determined by the black hole's mass and spin. The ring-down signal encodes information about the final black hole's properties, allowing observers to measure its mass and spin from the gravitational wave signal alone. The energy comes from the orbital energy of the binary and from the rotational energy of the black hole's spins. As the black holes spiral together, their orbital energy decreases. They fall deeper into each other's gravitational wells. This energy doesn't disappear. It converts to gravitational waves. The faster the orbital motion, the more efficient the conversion. In the final seconds before merger, when orbital velocities approach significant fractions of light speed, the conversion efficiency peaks. Spin energy also contributes. Supermassive black holes rotate, often rapidly. The Kerr solution to Einstein's equations describes rotating black holes and shows they can spin at up to a specific maximum rate, beyond which they would cease to be black holes. Many supermassive black holes spin at rates approaching this maximum. When two spinning black holes merge, The alignment of their spins relative to the orbital plane determines how much spin energy converts to gravitational waves. If the spins are aligned with the orbital angular momentum, the merger is relatively gentle, and the final black hole rotates rapidly. If the spins are misaligned or counteraligned, the merger is more violent, more energy converts to gravitational waves, and the final black hole may rotate more slowly. The most extreme case, two black holes of equal mass with spins anti-aligned in the orbital plane, can convert up to 11% of the total system mass to gravitational wave energy. The practical consequence is that these mergers are among the most energetic events in the universe. Only the Big Bang itself releases more energy in a given volume of space. Unlike supernovae, which also release tremendous energy but mostly in neutrinos that escape unseen, black hole mergers release their energy in a form gravitational waves that propagates through the universe and carries information about the event. OJ 287, a binary in action. 4 billion years ago, when life on Earth consisted of nothing more complex than single-celled organisms, two supermassive black holes in the constellation Cancer were beginning their gravitational dance. The photons from their earliest interactions began their journey across space. They arrived at Earth in the late 19th century, when astronomers were just beginning to photograph the sky. Photographic plates from 1887 show OJ 287 as an unremarkable point of light. But astronomers noticed something unusual as they accumulated observations over decades. The object brightened periodically. Roughly every 12 years, it flared dramatically, often showing a double-peaked outburst pattern. The flares weren't identical, some were brighter than others, and the timing varied by a year or two, but the overall pattern was unmistakable. By the 1980 seconds, a century of observations revealed a clear 12-year cycle. In 1988, astrophysicists Imo Silanpa and colleagues published a radical proposal. OJ 287 contains a binary supermassive black hole system. The 12-year period represents the orbital period. The double-peaked outbursts occur because the smaller black hole passes through the accretion disk of the larger black hole twice per orbit, at periapsis and at a second disk crossing on the opposite side of the orbit. This interpretation explained many features of the observations. The optical flares occur when the smaller black hole plunges through the disk, heating gas to millions of degrees through shock heating and friction. The heated gas radiates across the spectrum, from radio waves to X-rays. The flares are luminous enough to outshine a trillion suns. About a year later, as material from this interaction flows down the accretion disk and falls into the black holes, a second peak occurs, dominated by synchrotron radiation from relativistic jets. Detailed modeling of the light curve by Mauri Valtonen and colleagues refined the orbital parameters. The primary black hole, they calculated, contains 18.35 billion solar masses, making it one of the most massive black holes known. The secondary contains roughly 150 million solar masses, itself larger than most galactic center black holes. They orbit each other once every 12 years, at a separation varying from 9 to 38 astronomical units. The orbital eccentricity is extremely high, with the orbit being strongly elliptical rather than circular. The orbital plane precesses due to general relativistic effects. This precession, the slow rotation of the orbit's orientation, amounts to about 40 degrees per 12-year period. This is comparable to the relativistic precession of the Hulse-Taylor binary pulsar, but observed at cosmological distances. The precession affects the timing of disk crossings, creating the slight variations in outburst timing that make precise predictions challenging. The team made specific predictions for when outbursts should occur based on the orbital model. In 2005, 2007, and 2019, the predicted outbursts occurred within weeks of the predicted times. The 2007 event was particularly important. A bright flare appeared on the 13th of September. 2007. Just one day after the prediction, the 2019 event confirmed the model again. But in 2022, a predicted outburst failed to materialize. Stephanie Kamasa at the Max Planck Institute for Radio Astronomy led an extensive observing campaign looking for the outburst. Multiple telescopes monitored OJ 287 throughout the predicted window. The outburst didn't occur. This non-detection challenged the binary model. Several explanations have been proposed. Perhaps the orbital parameters need refinement. Small differences in mass or spin could shift the timing. Perhaps the accretion disk structure changed, making the interaction less luminous. Or perhaps the binary model itself requires modification. Alternative models exist. Marina Butuzova and Alexander Plavin proposed in 2021 that OJ 287 might contain a single black hole rather than a binary. In this model, the 12-year periodicity arises from precession of a helical jet. The jet's viewing angle changes periodically due to Lense-Thirring precession caused by the black hole's spin. When the jet points more directly at Earth, we see enhanced Doppler boosting, and the object appears brighter. This debate illustrates science in action. Multiple models can fit observations up to a point, but they make different predictions for future observations. The 2022 non-detection falsified, or at least challenged, some versions of the binary model. If the binary model is correct, but requires parameter adjustments, future outbursts should occur on a modified schedule. If the single black hole model is correct, a different pattern should emerge. Recent observations with radioastron and ground-based radio telescopes captured the structure of OJ 287's jet in unprecedented detail. The images show a ribbon-like jet structure. This morphology is consistent with a precessing jet, but doesn't definitively distinguish between the binary and single black hole scenarios. Regardless of which model ultimately proves correct, OJ 287 demonstrates the complexity of supermassive black hole systems. Whether it's one black hole or two, the environment is extreme powerful magnetic fields, relativistic jets, accretion disks with internal temperatures exceeding 10 million degrees, gravitational fields strong enough to distort spacetime significantly. For the binary model, OJ 287 represents a later stage of evolution than most observable binaries. At a separation of 10 to 40 astronomical units and a 12-year period, the system has crossed the final parsec and is well into the gravitational wave-dominated regime. If the binary model is correct, OJ 287 will merge within 10,000 years, an eye blink in cosmic terms. The kick. When two black holes merge, something remarkable can happen. The newly formed black hole can receive a kick, a recoil velocity that sends it flying through space. In extreme cases, this kick can be powerful enough to eject the black hole from its host galaxy entirely, casting it out to wander the intergalactic void. The physics behind gravitational wave recoil is subtle but inexorable. When a binary system emits gravitational waves asymmetrically, more strongly, in one direction than others, the system recoils in the opposite direction to conserve momentum. It's analogous to a rocket, where ejecting mass in one direction propels the rocket in the opposite direction, but with gravitational waves instead of exhaust. For equal mass black holes with no spin, the gravitational wave emission is nearly symmetric. The binary emits comparable power in all directions. Small asymmetries arise from the orbital motion, producing a beaming effect where waves are slightly stronger in the direction the smaller black hole moves. This generates modest recoil velocities, typically around 170 kilometers per second. But when the black holes have different masses or spins, the asymmetry increases dramatically. This enhances the beaming effect. For mass ratios of 2 to 1 or 3 to 1, recoil velocities can reach several hundred kilometers per second. Spin introduces another dimension of complexity. black holes can rotate up to a theoretical maximum determined by general relativity. When spinning black holes merge, the orientation of their spins relative to each other and to the orbital plane determines the gravitational wave emission pattern. Certain configurations produce highly asymmetric emission. The most extreme case occurs when two equal mass black holes have spins anti-aligned in the orbital plane, spinning in opposite directions perpendicular to the orbit. Numerical simulations by multiple teams, including work by Manuela Campanelli, Carlos Lausto, Josef Zlochauer, and David Merritt, showed these configurations can produce superkicks, reaching 5,000 kilometers per second. 5,000 kilometers per second is roughly 11 million miles per hour. This exceeds the escape velocity of even the most massive galaxies. A typical large galaxy has an escape velocity around 1,000 kilometers per second at its center, decreasing with distance from the center. A black hole receiving a 5,000 kilometer per second kick would shoot out of the galaxy like a bullet. The consequences are profound. An ejected, supermassive black hole takes with it any closely bound stars and gas, creating a hypervelocity compact object racing through intergalactic space. But most of the surrounding matter, the accretion disk, the broader stellar population gets left behind. The ejected black hole becomes essentially invisible, no longer accreting gas and producing light. Astronomers have found candidate recoiled black holes. One of the best cases is CXOJ 101527 2+6 25911, discovered through Chandra X-ray Observatory observations. The object shows X-ray emission offset from the center of its host galaxy by several thousand light-years. The emission spectrum suggests a supermassive black hole still accreting some residual gas. The offset position and velocity are consistent with a black hole that received a kick during a merger tens of millions of years ago and is now leaving the galaxy. Another candidate is 3C 186, a quasar discovered by Hubble Space Telescope observations. The quasar, the actively accreting supermassive black hole, sits about 35,000 light-years from the center of its host galaxy and is moving at 2,000 kilometers per second relative to the galaxy. Marco Chiaberge and colleagues proposed this black hole received a gravitational wave kick during a recent merger and is in the process of being ejected. For stellar mass black holes, recoil has different implications. When stellar mass black holes merge in dense environments like globular clusters, compact groups of hundreds of thousands of stars, even modest kicks can eject the remnant. Globular clusters have escape velocities around 50 kilometers per second. A post-merger kick of 200 kilometers per second sends the black hole flying out of the cluster. This affects black hole demographics. If every merger in a dense environment leads to ejection, then clusters can't build up populations of massive black holes through repeated mergers. This places limits on how massive stellar mass black holes can grow in clusters. It also means that the black holes LIGO detects might have formed in different environments with different ejection probabilities. In January 2020, LIGO and Virgo detected GW 200129, a merger between two black holes of unequal masses, one about 32 solar masses, the other about 20 solar masses. The orbital plane precessed during the inspiral, causing the gravitational wave signal to show characteristic modulations. This precession indicated high spin, and high spin in unequal mass mergers typically produces significant kicks. Vijay Varma at the Max Planck Institute for Gravitational Physics led an analysis of GW 200129 that measured both the magnitude and direction of the recoil for the first time. The analysis showed the remnant black hole received a kick velocity exceeding 50 kilometers per second. The direction pointed at an angle relative to the line of sight to Earth, which could be inferred from the gravitational wave signal's properties. A kick of 50 kilometers per second is fast enough to eject the remnant from a globular cluster, but not from a galaxy. However, It represents only a lower limit. The actual kick could be larger. The measurement uncertainty and the orbital inclination relative to our line of sight mean the true kick could reach 100 kilometers per second or more. The ability to measure recoil velocity and direction from gravitational wave signals opens new possibilities for understanding black hole populations. Different formation scenarios produce different kick velocity distributions. Black holes forming in dense stellar clusters and merging there should show evidence of kicks. Black holes forming in isolation or in less dense environments might show different patterns. For supermassive black holes, recoil affects galaxy evolution. A kicked black hole that remains bound to its galaxy but displaced from the center will eventually sink back toward the center through dynamical friction, but this takes tens of millions of years. During this time, the galaxy has a displaced active nucleus. Observations of offset active galactic nuclei provide clues about recent merger history. A black hole ejected from its galaxy entirely represents a significant loss of mass from the galactic center. This affects the galaxy's structure, the motions of stars in the core, and the possibility of future black hole growth through accretion. Galaxies that have experienced multiple mergers with kicks might have smaller central black holes than expected based on their stellar mass. The probability of extreme kicks depends on black hole spin. If black hole spins are randomly oriented, superkicks are rare because they require specific spin alignments. If galaxy merger dynamics tend to align black hole spins with the orbital plane, as some simulations suggest, then superkicks become more likely. Current observations don't yet definitively resolve which scenario is more common, but future gravitational wave detections will clarify this. The aftermath. When the final merger occurs, two black holes become one. The event horizon, the boundary beyond which nothing can escape, elongates and stretches during the merger, briefly forming an exotic shape before settling into the perfect sphere or oblate spheroid characteristic of a stable black hole. The newly formed black hole carries the combined mass of its progenitors, minus the few percent converted to gravitational wave energy. If two black holes of 100 million and 90 million solar masses merge with 5% efficiency, the result is a 180.5 million solar mass black hole, with 9.5 million solar masses of energy radiated as gravitational waves. The final black hole also carries angular momentum spin, determined by the spins of the progenitors and the orbital angular momentum of the binary. If the progenitor spins were aligned with the orbital angular momentum, they add together, producing a rapidly spinning remnant. If they were misaligned, some of the angular momentum converts to gravitational wave emission, and the remnant spins more slowly. For a few seconds to a few hours after merger, the remnant undergoes ringdown. The event horizon oscillates in characteristic modes, like a bell ringing after being struck. These oscillations emit gravitational waves at specific frequencies determined entirely by the mass and spin of the final black hole. By detecting and analyzing the ringdown signal, observers can measure these properties with remarkable precision. Stephen Hawking proved in 1971 that the surface area of a black hole's event horizon can never decrease in any physical process. This area theorem is a classical analog of the second law of thermodynamics. When two black holes merge, the surface area of the final black hole must equal or exceed the sum of the areas of the progenitors. In 2021, LIGO scientists analyzed gravitational wave data from the GW150914 merger to test this theorem. They measured the surface area before and after merger, finding the area increased by 1.4 times 10 to the 68th square meters, consistent with the theorem. This provides another test of general relativity in the strong field regime. The merged black hole may be displaced from the galactic center if it received a significant recoil kick. Even a modest kick of a few hundred kilometers per second places the black hole several hundred light-years from center. From this offset position, the black hole experiences the galaxy's gravitational field and begins to sink back towards center through dynamical friction. The timescale for return depends on the kick velocity, the black hole mass, and the galaxy's central stellar density. For typical parameters, sinking times range from 10 million to 100 million years. During this period, the galaxy has a displaced active nucleus if the black hole continues accreting. Observations of offset quasars and active galactic nuclei provide constraints on kick velocities and galaxy dynamics. The accretion disk around the binary doesn't instantly disappear at merger. Some disk material remains bound to the merged black hole and continues accreting. But the merger disrupts the disk structure. Shock waves and turbulence heat the disk. Some material may be ejected in winds or jets. The accretion rate varies as the disk settles into a new equilibrium around the single black hole. This produces observable electromagnetic signatures. The merger itself might generate a bright flare as tidal forces from the coalescing black holes disrupt the inner disk. The subsequent months to years might show variable luminosity as the disk reorganizes. Eventually, accretion settles into a steady state, and the system resembles a typical single supermassive black hole with accretion disk. The surrounding stellar population also adjusts. The binary carved out a depleted core during its inspiral. After merger, this core begins to refill as stars on distant orbits return to the central region. Stars passing near the merged black hole receive gravitational slingshots that redistribute orbital energy and angular momentum. Over hundreds of millions of years, the stellar distribution approaches a new equilibrium. Galaxy mergers often trigger starbursts, periods of intense star formation as gas clouds collide and compress. The starburst typically peaks hundreds of millions of years before the black holes merge, when the galaxies first collide and their gas-rich disks interact. By the time the black holes merge, the starburst has often faded and the galaxy is settling into a post-merger configuration. The merged galaxy in the Milky Way Andromeda case, nicknamed Milkomeda, will be an elliptical or lenticular galaxy, depending on the merger geometry and gas content. Elliptical galaxies typically have older stellar populations and little ongoing star formation, shaped by their merger history. The merged black hole at the center will be more massive than either progenitor, ready to grow further through accretion or another merger if the galaxy undergoes another collision. This cycle repeats throughout cosmic history. Galaxies merge, their black holes merge. The merged galaxy eventually merges with another galaxy. The black holes merge again. Each merger builds more massive black holes and more massive galaxies. The largest galaxies in the universe, giant ellipticals in the centers of galaxy clusters, containing trillions of stars, are products of many mergers. Their central black holes, sometimes exceeding 10 billion solar masses, grew through both accretion and mergers over cosmic time. The cosmic context: the universe is 13.8 billion years old. In that time, structure has grown from nearly uniform conditions shortly after the Big Bang to the rich cosmic web of galaxies, galaxy clusters, and filaments we observe today. This growth occurred hierarchically, small structures forming first, then merging to build larger structures. The first stars formed a few hundred million years after the Big Bang. These population 3 stars, containing only hydrogen and helium with no heavier elements, were likely very massive and short-lived. When they exhausted their nuclear fuel and collapsed, they left behind black holes, the seeds of today's supermassive black holes. But growing a black hole from 100 solar masses to a billion solar masses through accretion alone requires sustained accretion at high rates for hundreds of millions of years. Observations of quasars at redshifts above 7, less than 800 million years after the Big Bang show billion solar mass black holes already existed. Growing them purely through accretion seems challenging, though not impossible. Mergers provide an alternative growth channel. If early black holes merged frequently, they could grow to supermassive sizes more quickly than through accretion alone. A 100 solar mass black hole that merges with another 100 solar mass black hole becomes 200 solar masses. Merge again and reach 400 solar masses. After 20 mergers, you reach 100 million solar masses. The question is whether such rapid merger sequences are realistic. Each merger requires the black holes to find each other, which requires being in the same galaxy. This means the black holes host dark matter halos must merge. In the early universe, structure formation was rapid. Small halos merged frequently, building larger halos. Black holes in these merging halos would eventually encounter each other. Cosmological simulations track this hierarchical growth. Modern simulations follow the evolution of hundreds of millions of particles, representing dark matter, stars, and gas, from shortly after the Big Bang to the present. They include physics of star formation, black hole accretion, feedback from supernovae and active galactic nuclei, and galaxy mergers. These simulations show that galaxy mergers are common, especially at high redshifts when the universe was younger and denser. Typical galaxies undergo several major mergers with comparable mass galaxies over cosmic history. They undergo many more minor mergers with smaller galaxies. Each major merger should bring the central black holes together. The rate of supermassive black hole mergers depends on the galaxy merger rate and on whether the black holes actually merge after their host galaxies merge. The Final Parsec Problem suggested they might not, but the NANOGrav detection shows they do. Taking this into account, theoretical estimates suggest hundreds of thousands of supermassive black hole binary mergers occur throughout the observable universe every year. Each merger produces gravitational waves that propagate outward at light speed. By the time these waves reach Earth, they've traveled millions or billions of light years. The waves from nearby mergers, cosmologically nearby, meaning within a few 100 million light years, arrive with relatively large amplitudes. Waves from distant mergers arrive weakened by distance. The gravitational wave background detected by NANOGrav represents the combined signal from all these mergers. Nearby loud sources contribute more to the signal, but there are few of them. Distant quiet sources contribute less individually, but there are vastly more of them. The overall spectrum, how signal strength varies with frequency, encodes information about the mass distribution of merging black holes and the cosmic merger rate. The observed spectrum shows slightly more power at low frequencies than the simplest models predict. This red spectrum could indicate that supermassive black holes are more massive on average than expected, or that environmental effects like gas or dark matter influence the late stages of inspiral. It could also indicate contributions from exotic sources like cosmic strings or phase transitions in the early universe, though black hole mergers remain the most plausible explanation. Over the next decade, pulsar timing arrays will accumulate more data, increasing sensitivity and potentially detecting individual loud sources. These detections will test models of binary evolution, measure properties of specific systems, and provide targets for electromagnetic follow-up observations. In the 2030 seconds, the Laser Interferometer Space Antenna LISA will launch. LISA consists of 3 spacecraft flying in formation 5 million kilometers apart, forming a triangular interferometer. This configuration will detect gravitational waves at frequencies between 0.1 MHz and 0.1 Hz, bridging the gap between pulsar timing arrays and LIGO. LISA will detect supermassive black hole mergers throughout the universe. For mergers with total masses above 10 million solar masses within several billion light years, LISA will detect the final weeks or months of inspiral and the merger itself. For certain nearby massive binaries, LISA might detect them years before merger, watching them evolve in real time. Combined observations with LISA and electromagnetic telescopes will test general relativity with unprecedented precision. The gravitational wave signal depends only on the masses and spins of the black holes and the distance to the source. The electromagnetic signal depends on the environment, gas, stars, magnetic fields. Comparing the two probes, both the black holes and their surroundings, the future of gravitational wave astronomy is bright. Each detection adds to our understanding of how structure formed, how galaxies evolved, how black holes grew to their current sizes. Cosmic witnesses, we live in a remarkable moment in cosmic history. For billions of years, gravitational waves from merging black holes traverse the universe undetected, invisible ripples passing through galaxies and stars and planets with no trace. For nearly the entire history of life on Earth, these waves arrived unnoticed. Even after humans developed technology, even after we understood the universe contained galaxies and black holes, even after Einstein predicted gravitational waves existed, we couldn't detect them. Then, on the 14th of September, 2015, that changed. Two black holes merged, 1.3 billion light-years away. The gravitational waves from their merger waves that began their journey when complex life on Earth consisted of algae and simple multicellular organisms passed through the LIGO detectors, stretching and squeezing space by 1 part in 10 to the 21st power. The detectors registered the signal. Humanity heard, for the first time, the sound of spacetime itself vibrating. Since then, we've detected hundreds of events. We've learned that black hole mergers are common. We've measured black hole masses and spins. We've tested general relativity in regimes Einstein never imagined. We've detected neutron star mergers and observed their electromagnetic counterparts, seeing both gravitational waves and light from the same event. And in 2023, pulsar timing arrays detected the gravitational wave background from supermassive black holes. The cosmic hum produced by hundreds of thousands of mergers throughout the universe is now audible to our instruments. We're witnessing the accumulation of billions of years of galactic evolution, compressed into a signal we can measure and analyze. The questions we can address with gravitational waves extend far beyond black holes. Dark matter, that mysterious substance comprising most of the universe's mass, might interact with itself, and if it does, that interaction might solve the Final Parsec Problem. Testing this hypothesis requires precisely measuring the gravitational wave spectrum from supermassive black hole mergers and comparing it to predictions from different dark matter models. Galaxy formation models predict merger rates as a function of cosmic time. Measuring the actual merger rate with gravitational waves tests these models, revealing whether our understanding of hierarchical structure formation is correct. Finding discrepancies would indicate missing physics in our models, perhaps related to dark energy, modified gravity, or something entirely unexpected. The nature of black holes themselves remains mysterious, despite decades of study. General relativity predicts black holes are characterized entirely by 3 numbers: mass, spin, and electric charge. Astrophysical black holes are electrically neutral, so only mass and spin matter, but quantum gravity theories suggest black holes might be more complex, perhaps carrying additional properties beyond mass and spin. Testing the no-hair theorem requires precise measurements of black hole ring-down signals. The oscillation frequencies of a black hole depend on its mass and spin in specific ways predicted by general relativity. Detecting deviations would indicate new physics, perhaps quantum corrections to general relativity or entirely new theories. The universe continues its evolution. Right now, supermassive black hole binaries at every stage of evolution exist throughout the cosmos. Some have just formed through recent galaxy mergers, their host black holes still millions of light years apart. Others have spiraled to separations of thousands of light years, beginning to form bound binaries. Still others are crossing the final parsec, their fates determined by the interplay of stars, gas, and perhaps dark matter. And somewhere in the universe, every few months, a binary completes its merger. Two black holes coalesce. Gravitational waves carry energy away. A new, more massive black hole forms. The event horizon settles into equilibrium. The galaxy adjusts to its new configuration. The cosmic cycle continues. Whether or not the Milky Way and Andromeda collide in our cosmic future, galaxy mergers are happening throughout the universe right now. Black holes are spiraling together, crossing that final parsec, emitting gravitational waves and merging in brilliant releases of energy. The story we've explored tonight isn't about a single possible collision billions of years away. It's about a fundamental process that has shaped every large galaxy in the cosmos, including our own. Our galaxy has merged with others before. The scars of those ancient collisions remain visible in stellar streams and disrupted dwarf galaxies. Sagittarius A times itself likely grew through past mergers, each one adding to its mass. Whether it merges again with Andromeda's black hole or continues its solitary existence at our galactic center, it stands as testament to the violent processes that shaped our cosmic home. But for now, we are here. We have built instruments sensitive enough to detect these cosmic events. We have developed theories sophisticated enough to predict and explain them. We've achieved something our ancestors could never have imagined. We've measured the vibrations of space-time itself. As you drift towards sleep, consider this. Somewhere in the observable universe, roughly 46 billion light-years in radius, millions of supermassive black hole binaries are spiraling toward merger. Their gravitational waves are traveling toward us even now. Some will arrive tomorrow. We are immersed in a sea of gravitational waves, ripples from cosmic events stretching back to the Big Bang itself. Most pass through us undetected, too weak or at the wrong frequency for our current instruments. But we're learning to sense them, to decode them, to read the information they carry about the universe. The titans are colliding. They've been colliding for billions of years. They'll continue colliding for billions more. And we briefly, wonderfully, are here to witness it. If you've enjoyed this journey through cosmic collisions, consider subscribing to join future explorations of the universe's deepest mysteries. There are so many more stories waiting among the stars. Sleep well. The universe continues its ancient dance, indifferent to our attention, yet somehow more meaningful for having been observed, even briefly, by minds evolved on a small planet, orbiting an ordinary star in an unremarkable galaxy. The cosmos is vast, violent, beautiful, and we are part of it.